Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi everyone. Thank you for staying with us and keep exploring the transitions of information in the 5th Iclad. I'm Zarif, your host for the next 1 hour. Today is the 3rd day of the conference. I believe a lot of inputs a lot of input that we have gathered from keynote session, forum, industrial technical paper and mini classes. For today, do stick to your screen as we are going to explore an interesting topic on innovation in solar energy application, hybrid photovoltaic thermal solar technology. We will start in just a few minutes with our keynote speaker session, and if you have any question about the topic, you can go to the pigeonhole link which is available on your right side screen. We will have a little chat after the session to answer your question. So do ask questions and stay tuned till the end of these sessions. Before we proceed, just a little bit about our honorable keynote speaker, Professor Datuk Technology Dr. Kamaruzzaman Sofyan. Professor Datuk graduated with the Bachelor Studies in Mechanical Engineering from the University of Wisconsin-Madison, and after that he further studies for Masters in Energy Resources, University of Pittsburgh, and complete his study at PhD level in Mechanical Engineering from the Dargan Solar Laboratory, University of Miami Coral Gables. His main contributions are in a solar radiation modeling and resource assessment, advanced solar photovoltaic system that covers topic on grid-connected photovoltaics, solar power regenerative fuel cells, solar hydrogen production, thin film silicon solar cells. An advanced solar thermal system that covers solar cooling, solar heat pump power, solar assisted drying, combined photovoltaic thermal and hybrid collector. He also holds several patents for his innovation in renewable energy technologies. The innovation and invention in renewable energy technologies have won special awards in international innovation and invention competition. He was conferred the Darjah Datuk Paduka Mahkota Perak by His Royal Highness the Sultan of Perak in 2013, a Fellow of Malaysia Academics of Science, and listed in the 2019 and 2020 highly cited researchers by the Web of Science Group, Clarivates Analytics. Without further ado, let's invent it now. Presented to you, Professor Datuk Technologist Dr. Kamaruzzaman Sofyan.
Assalamualaikum warahmatullahi ta'ala wabarakatuh. Thank you very much for inviting me to this conference. I will be presenting on a technology that improves the output from PV from merely 20% to over 80%. The technology is known as hybrid photovoltaic thermal technology, or hybrid PVT. In addition, hybrid PVT technology produces both electrical as well as thermal energy simultaneously, hence opening the door to various applications. The contents of the presentation will begin with the current development of PVT technology and the applications, followed by some advanced concept of cooling in PVT, and also the future direction in the research, development, and application of PVT technology. Solar radiation is one of the primary resources of energy and is classified into the direct solar energy, stored solar energy, and indirect solar energy. The direct solar energy can be classified into PV and thermal. PV is the direct conversion of sunlight into electricity, and solar thermal is the direct conversion of sunlight into thermal energy. Moreover, the stored solar energy can be classified into renewables such as biomass and non-renewable such as fossil fuel. Finally, the indirect solar energy can be further classified into wind energy and hydropower. Energy resources from the direct solar energy is enormous and is environmental friendly form of renewable energy. The red dot represents the world total annual primary global energy consumption. The annual solar radiation on Earth's surface is over 10,000 times the red dot, which means that the total annual global primary energy consumption is less than the solar radiation incident at the Earth's surface in just 1 hour. Silicon-based solar cell occupies 90% of the PV market in the world, followed by thin film solar cell, about 10% of the market. Thin film solar cell available in the market are the CAD telluride or the cadmium telluride and the CIGS. The organic solar cell is still not in the market as of now. An example of promising organic solar cell are DSSC or the dye-sensitized solar cell and the perovskite solar cell. Over 80% of the PV system are grid connected, which means then more than 50% are for central system, while over 30% are for distributed system. Furthermore, 14% are off-grid systems for rural electrification as well as for remote areas applications. The cumulative installed capacity of PV has reached beyond the 1,000 gigawatt level and is expected to reach a value of 1,500 gigawatt in 2030. The panel efficiency is determined on various factors such as the cell design, N or P type, silicon wafers, and the cell layout. In addition to that, it depends also on the configuration as well as panel size. The average panel conversion efficiency now has increased from 50% to well over 20%. And this resulted in power ratings of standard panel to increase from 250 watts to 400 watts. Panel built using advanced IBC or interdigitated back contact solar cells are the most efficient, followed by the heterojunction or the HJT cell, and then followed by the half-cut multi-bus monocrystalline PERC cell, and also by the shingled cells. Most cell, example the silicon-based solar cell, suffers from a drop in efficiency with increased cell temperature. Each Kelvin increase in cell temperature reduces the efficiency by up to 0.5%. Therefore, heat removed from the PV cell can basically lower the temperature and thus increase the cell efficiency. Other benefits from lowering the operation temperature is the improved lifetime of the PV cell. The opportunity for PVT application can be seen from the solar spectrum. The electrical gain from PV is more than 20%. However, the largest share of the solar spectrum, about 70%, is converted into heat, hence increasing the temperature of the modules. The rest are reflected. PVT collectors, on the contrary, are engineered to transfer heat from the PV cells to a fluid, thereby cooling the cell and thus improving the efficiency. In this way, excess heat can be made useful and can be utilized in terms of various applications of industrial process heat, such as water heating and space cooling, and also for heat pumps application. There are basically three types of PVT, namely the liquid PVT, which is a conventional flat plate heat collector with integrated PV on the absorber. Next is the PVT air-based collector. These are, for example, facade or roof integrated PV cells with ventilation air pass behind or in front of the PV cell. And finally, the combi PVT, which is the combination PVT. The PVT that simultaneously produce hot air, hot water, and also electricity. If the solar thermal and PV are placed side by side, the thermal solar collector has an efficiency on the average about 60%. And the electrical efficiency from PV is about 20%. The area of the collector is the sum of the area of the solar thermal and the photovoltaic collectors. Hence, the combined photovoltaic thermal efficiency is about 40%. On the other hand, if solar thermal collector and PV are combined and the area occupied by both solar thermal and PV are the same, the solar thermal collector has an efficiency on the average about 60%. And the PV efficiency is about 25% because there is cooling of the PV panel. Hence, the combined PVT efficiency is 85%. Now, the rationale of using PVT is shown in this slide. In this illustration, as you can see from the left side of the slide, PVT are not used, but the PV panel and the thermal panel are used separately. The size of the PV is about 13 meters square, and the solar thermal is about 29 meters square. Therefore, the average annual thermal yield is about 22 megawatt hour, and the annual electrical yield is about 2.5 megawatt hour. In a PVT system, as you can see on the right of the slide, the annual thermal yield is about 22 megawatt hour, is the same, but the area becomes bigger to 42 meters square. In addition to that, the annual electricity yield will increase to 5.8 megawatt hour. Hence, if you add up the solar thermal and electricity yield per square meter, you will see that the PVT roof generates 33% more kilowatt hour of solar energy. This is a case of a housing complex in Switzerland in the Alpine region. This particular complex is comprised of 3 identical multi-family buildings. Each building has the same highly efficient building envelope, the same number of flats, and a heat pump that relies on a storage system. Therefore, as you can see from here, that PVT has the highest output when adding together the thermal and electricity yield across the roof covered by the solar system. In Europe, PVT has also been used for air cooling and also for space heating. PVT is also used to provide electricity and heat to over 162 occupants in a building in Spain for the elderly. PVT can also be combined in a single product, easy to be integrated on roofs or on facade or even under concentration. And another example of a PVT installation is a hotel in Spain composed of 90 PVT panels. PVT panels can also be used with concentrating collectors such as the one in Germany for cogeneration of power and heat. This is known as CPVT, where the primary concentration is by standard parabolic mirrors, and the secondary concentration is by tailor-made lenses. Here at UKM, we have built a low-energy house located in the campus in Bangi, which incorporate low-energy features including a double facade shading, passive ventilation, daylighting, and also PVT for domestic hot water as well as for electricity production. Some advanced concepts in cooling of PVT will now be presented. This concept will enhance the heat transfer from the PVT and will also increase the electricity production from the PVT unit. The PVT technology consists of flat plate water and air-based collector, and the combi type solar collector. The PVT with concentrating collector comprises of a Fresnel lens and compound parabolic collectors, or CPC, are the next type of technology of PVT. There are also PVT, which consists of some advanced design for cooling of PV, such as thermoelectrics, heat pipe, refrigerant-based, PCM or phase change material, and also nanofluids. The absorber tubes is an important component of PVT. To maximize the energy collection, the absorber plate of a collector usually is coated with material that has high absorptance for solar radiation and low emittance for re-radiated thermal energy. Such a surface is called selective surface. In addition, the design of the absorber is so important to maximize absorption as well as to optimize wetted surface for enhancements of heat transfer. A PVT grid-connected photovoltaic system, or grid-connected PVT system, is an electrical generating solar power system that is connected to the utility grid with additional thermal energy production. An experimental unit was set up at the UKM campus for demonstration of a grid-connected PVT system. The electricity is connected to the local UKM grid. Nanofluids are used in PVT collectors. Nanofluid are new class of nanotechnology-based heat transfer fluid obtained by dispersing and stable suspension of nanoparticle with typical dimension in the order of about 10 nanometers. Nanofluid can improve thermal physical properties compared to the base fluid. And the Brown movement is the key mechanism basically governing this thermal behavior of the nanofluids. Nanofluid can be prepared using the two-step method, which, for example, uses nanofluids such as silicon carbide to be included as nanoparticle to a base fluid. And subsequently, it goes through an ultrasonification process. The other nanofluid can be silicon dioxide or titanium oxide, or even a combination of it, which we call binary nanofluids. The energy production from a grid-connected PVT system using nanofluid, for example, using silicon carbide as the nanoparticle, exceeded the performance of a grid-connected system, PV system, due to the enhancement in heat transfer. For example, there is an increase of performance about 30% compared to the system of an ordinary or conventional grid-connected system. The next design of PVT is using nanofluid and nano-PCM. The PVT composed of two parts, which are the PV module itself and the nano-PCM tank, which encloses the copper pipe which carries the nanofluid. Glass wool was used as insulation, and in between the PV and the nano-PCM tank, there is a layer of silicon oil which is used to eliminate air gaps and increase heat transfer. This is how actually the integrated PV panel looks like, which has the nano PCM tank as well as the copper pipes which the nano fluid enters, and this actually enhances the heat transfer in the PVT. The evolution of the PVT panels from water-based to nano fluid with nano PCM is shown here. It increases from 60% for the water-based PVT to 74% for the nano fluid-based PVT, and finally to 85% for the nano PCM and nano fluid-based PVT. The PV panel used here has an efficiency about 7 to 8%. When nano fluids and nano PCM are included, the power of the PVT increases from 61 watts to almost 120 watts. This shows an almost 50% increase in power. The efficiency also increases to about 14%. The electrical and thermal efficiency of this system compared to the others, this is probably one of the highest that you can see in the literature. The economics for conventional grid-connected system, grid-connected with FIT of ringgit 20 cents per kilowatt hour, and there's no more FIT right now, but this is for comparison. Also for PVT with water, PVT with nanofluids, and PVT with nanofluids and nano PCM can now be compared. The conventional grid-connected system has over 13 years payback period. The grid-connected system with the FIT has a payback period about 5 years, but the system with the nanofluid and nano PCM has a payback period about 7 years. How fast do solar panel degrade? On the average, solar panel degrade at the rate about 1% each year. That's backed up by solar panel manufacturer's warranty, which guarantees 90% production in the first 10 years and also 80% production by year 25th and the 30 years. Now, the energy yield is important. For example, in a solar farm, mortgage payment has to be met. The degradation impact on the energy yield in a 8 megawatt solar farm, for instance, is more than 1%, for example. Now, cooling of the PV panel will basically enhance the energy gain, and thus income generated from the panel can also be increased, and PVT is promising system that accomplish this. Spectral splitting has emerged as a promising route towards next generation high performance PVT collectors. And nanotechnology plays an important role in meeting the optical and thermal requirement of advanced spectral splitting collector design. Nanofluids and nanofilms are currently the most common nanomaterials used for splitting PVT systems. The efficiency limits of spectral splitting PVT collectors is significantly higher than that of the standalone PV panels. The stability of nanomaterials filters remain a critical challenge for their long-term employment. Another concept in is the jet impeachment PVT, which provide effective and flexible way to transfer energy or mass in any industrial applications. Another concept of cooling of PVT is using fins. The increasing in PV module temperature can also be partially avoided by extracting the heat using suitable cooling system with using different fins configuration. Fins or extended surface were used to enhance heat dissipation. The heat dissipation via fins or these extended surfaces significantly improve cooling performance by providing additional surface area for heat transfer. Fins are thus used whenever the available area is found insufficient to transfer the required quantity of heat with the available temperature gradient and heat transfer coefficient. In the case of fins, the direction of heat transfer by convection is perpendicular to the direction of conduction of heat flow. Another concept of cooling of PVT is the thermoelectric generator, also known as TEG. It is also known as a seebeck generator. It is a solid-state device that converts heat flux or temperature differences directly into electrical energy through a phenomenon called the seebeck effect, which is a form of thermoelectric effect. The seebeck effect is a phenomenon in which a temperature difference between two dissimilar electrical conductors or semiconductors produces a voltage difference between the two substances. When heat is applied to one of the conductors or semiconductors, heated electrons flow towards the cooler one. Another type of PVT is the air-based system, and usually it is used for drying of agricultural and marine products. A double-pass PVT with CPC and fins enhances the heat transfer and increases the efficiency of a solar drying system. Bifacial PV converts sunlight to DC electricity on both the front and back of the PV modules. And it can be used equally well with either a fixed slope or a tracking structures. Bifacial solar panels are more efficient than the monofacial panel, simply because they collect sunlight on either side. Many bifacial panel has 30% more power output compared to the monofacial panel. A bifacial PVT produces both electricity and thermal energy. The bifacial PVT produces an extra 50% more combined electricity and thermal power compared to the monofacial PVT panels. Finally, I will present the future direction of PVT. And the predominant PVT technology will still be the unglazed PVT, the covered or the glazed PVT, and for higher temperature application will be the concentrating PVT. PVT with air-based system can be integrated for facade, PV solar walls, solar dryers, space heating applications, and for space cooling. PVT-based system can be used for grid-connected PVT, with heat transfer enhancements such as the use of nanofluids, nano-PCM, CPC, and as well as fins. In addition to that, PVT can also be used for space cooling applications. There are several strategies for the widespread application of PVT. Number one is awareness and education program. This actually will create an international environment that enables and convince industry to develop PVT systems. And then if you look at the market, PVT system can compete with separate PV and solar thermal in terms of economics, in terms of aesthetic, and also in terms of comfort. Finally, as integrated product and system, PVT combine a PV panel and thermal collector into one system that can compete with non-renewable technologies. And to increase the efficiency of PVT, several activities can be undertaken. For example, from applying solar cell with higher absorption, improve heat transfer using enhanced heat transfer features, bonding techniques to minimize the heat resistance, to deposition of thin film PV on metal substrates so that the PV and absorber are fully integrated, and of course for building integrated applications. And for more information, we have authored a textbook on PVT that elaborates on the principles, on the design, and on the applications, and this can be obtained through Springer. Finally, I would like to thank you, for your attention, and I am honored to answer any question on PVT technology. Thank you very much.
Dato, for your interesting innovations sharing session just now. Okay, Prof. Dato, we will go for the question and answer. Before that, just some chit chat with Prof. Dato first. How do you feel today, Prof. Dato?
Excellent, I feel good, very good.
Yeah.
Thank you thank you again for inviting me to the conference.
Okay, thank you, Prof. Dato. Actually, it's a very, I'm very amazed with the innovation research that have been conducted by Prof. Dato actually. As we know, in PV industry right now, the limitation of space and also the limitation of land is something that a big concern for us actually. We don't have any others solution, especially in increasing the efficiency of the output of the PV itself actually. So with this invention, I believe we can harvest more energy by the solar power to, I can say that to sustain the especially towards the energy transition. So yeah, that, Prof. Dato?
Yes, you see,
Okay.
PV panels, they work very efficiently if they are at low temperature. And one of the way basically to improve the performance is actually through cooling. And there are many ways that you can cool it. It has to be done efficiently. Not only it will increase the production of the panel, it also will enhance the lifetime of the panel. So therefore, I have introduced a few concepts basically to cool down the photovoltaic panels. This includes as simple as blowing wind under the PV panel through the use of nanotechnology, basically on cooling of the PV panels. And you can see that we have a lot of solar farms and also building integrated photovoltaics under the large-scale solar program and the NAM program. So therefore, if anyone would like to basically enhance the power of the PV panel, and also to enhance the lifetime, this is one of the method that is very promising, promising to enhance your performance of your photovoltaic panels. And of course, if you do the maths, the calculation through it, you can see that when collectors are separately, if you put thermal collectors and PV collectors separately, the area of the collector is twice the amount. But the amount of energy generated is also not is the amount of generated by the PV panel and also the amount of generated by the thermal panel. But when you put them together and then you have a means of cooling it, you will enhance the production of the PV panel. In addition to that, you also have thermal energy to be used for various applications. Therefore, the combined photovoltaic thermal efficiency will be increased. And you can do that analysis using the first law of thermodynamics and also the second law of thermodynamics. You will see that the benefits of using PVT technology. In addition to that, I think if space is of paramount requirement, you can see that the advantage of this particular technology.
So it's a very great invention from your explanation there. So there are lots of questions that we receive from the pigeonholes and also from myself also. I have a question for Professor Dato also. Maybe we go for my question first lah. My question first before we go to the pigeonhole question. So my question here is, lately we heard about over the news issue on the power shortage supply happened in the Europe countries and several in Asia countries. This power shortage supply is contributed by high dependency or high penetration of RE in their countries. And in Malaysia currently, we are putting an aspiration to increase RE in the supply chains of generation, which is we targeted about 31% RE by 2025, Professor Dato'. Okay, how do you look into this scenario, and what we at national level can do to avoid the same issue occurs in our supply chains of generations?
Okay, RE is not only solar. RE is also biomass. RE is also hydro. RE is also wind energy. So therefore, in order to enhance the generation mix for a favorable renewable energy mix, you have to basically use all of this technology. And who decided is the economics. The economics will decide for it. This technology are not in competition with each other. They are in complementary with each other. They complement each other. So therefore, it is wise to use it in the proper manner. Having a mix of the most optimum mix of all the REs will actually contribute towards the reduction of the emissions and also contribute towards sustainable development. So therefore, there are a lot of carbon-free technologies that you can basically have in the mix of renewable energy. As far as for the country to achieve 31% by the year 2030, right? 2035,
yeah.
It is not an impossibility, because the use of solar through the NEMS, through the NEMS 3.0 program, we have 3 programs in that will basically cover some of it. But there's also other form of renewable energy, for example, the hydro and the biomass that should also be utilized in order to achieve that target. And I'm very positive that target will be met by the year 2035. But in addition to that, the target is one thing, but the overall carbon reduction is important. That target of the overall carbon reduction is a better key performance indicator rather than the mix of renewable energy.
Thank you, Prof. Prof. Dato', on the comments on that question. I believe with this invention also will increase the deduction of the carbon, since we increase the efficiency and the dependency of the coal plant and the gas plant will be reduced.
I just like to add that energy doesn't only come in the form of electricity. Energy also comes in the form of heat, which is actually a main source of, we need a main source of energy for it, because to produce heat is different from to produce electricity. Heat is used in many various applications, such as in various industrial process heat applications, for drying, for water heating, for space heating, even for space cooling. So therefore, we should also think energy not only in the form of electricity, but also in the form of other form of energy, such as heat, which actually will contribute also, but to, in the overall nation contribution to the climate change, the emission gas reduction, and therefore, we should also look into other aspects of energy, not only in electricity. In terms of that particular target that was actually stated was actually for electricity generation, but you can go for others. You can also contribute in terms of thermal energy, and this particular technology PVT, there are 2 different technology of cooling. One uses water to cool, the other uses some sort of water, but with some addition of nanoparticles and nanoparticles. Now, what happens is that you will increase the efficiency, because using nanofluids or nanoparticles, it basically will enhance the heat transfer. When you enhance the heat transfer, you will be cooling down the panel and enhance the efficiency. Using water alone, just water alone, and when you use water, and when you use the water to cool the PV panel, you have to strategically place the panel. It's not just putting water and just putting a hose and doing it. No, there are a few methods that you can use basically to run a very well designed absorber underneath the PV panel. You have to use various methods to use some mathematical model basically to look into what's the best way of fully wetted surface to wet the surface so that it touches basically the surface of the back panel, and you will enhance the cooling. Now, that sort of technology, you are going to have about 20% in terms of increase in performance. The other technology, when you use nanoparticles or nanofluid, it will enhance more the heat transfer. Enhancing the heat transfer will do a lot of justice to the panel in terms of cooling, in terms of enhancing the lifetime of the panel. So therefore, when you use with nanotechnology, nanoparticles, you expect an increase of about 30 or 35% more. In some cases, you have about nearly 40% increase in the performance if you use that. Now, how do you calculate the economics? The economic is simple. You have a system of PV with no cooling, and then you just buy it, and then you look it, you purchase it, and you sell it, through whatever NAMS program that you have with certain amount of price. You probably going to get back your money probably in term maybe about maybe 10 years or 11 years, depending on the price of the PV panel. But when you pull down the collector, it will basically increase, of course, the cost, capital cost. But the energy gain from putting that PVT technologies, whether it's using water or using nanofluids, will cover back. The energy gain will basically, the more energy you gain, the more electricity you sell. So therefore, the payback period for the water can be decreased to 7 years. But by using nanofluids, of course, you have to process the nanofluid. But the output power, the energy gain is high. Therefore, you can get back, and I've shown you from the graph, you can get back your money after maybe 6 or 5 years of operation. So therefore, this technology enhances the cooling. When you enhance the cooling, you sell more electricity. That's the whole idea of the technology. And then, of course, I've shown you various techniques of cooling. And innovation in terms of the cooling are not only the one I've shown. There are many. At the time that I'm talking now, there are many papers that publishes on aspects of cooling PV panel. Yeah. Even looking at the spectral response of the sun. Yeah, you can split because the sun comes with various many wavelengths. There are only a specific wavelength that the PV will utilize. Opening up to the rest will actually enhance what we call the other application of that particular PV panel. So there are also the use of thermoelectrics. Thermoelectrics are actually dissimilar device that when they are in contact and you have dissimilar temperature, it will create its own electricity, because this is actually the fundamental in terms of when you have two dissimilar semiconductor materials, they create even your hand, when you put together, if they are in different temperature, you create some micro current through it, and this is thermoelectrics. And imagine that the collector, on the average, when you put it outside, it's about 50 degrees. So therefore, you can actually utilize that temperature for many other various applications. And I think, and also in terms of cost effectiveness, it does make sense. But one thing to caution here is that we don't sell PVT panel just like that. It has to be customized. Yeah, there are companies that sell photovoltaic thermal collectors, but you can also customize your application according to the needs of your system or your facilities.
Okay, I believe that's the question for the part 1, which is maybe can we see back the question previously? Yeah, there are part 2, I believe.
Any installation done elsewhere. In my presentation, I've shown a few applications that was done in Europe. There's also in Japan. in Israel, and also we have some application here in Malaysia, that the particular low energy house that I've shown to you. And there are also interests from many to use this PVT technology in order to utilize simultaneously the heat that you needed, and of course also the electricity that is produced from the system.
Okay, thank you, Prof. I believe as we see that there are a lot of technique that can we apply in order to keep the PV panels in the optimum temperatures for the better performance. So for that we can harvest more energies, and of course it will compensate the can I say that investment that we put in order to install this kind of technologies. Okay, so for the next question from our pigeonhole, from Aina, this is an amazing innovation. Is the PVT's commercially available product in the market? What was its percentage additional cost to apply the PVT in existing solar panel system?
Okay, there are companies that produces PVT. Especially both water-based PVT. It means that this particular PVT technology produces both electricity as well as hot water for various industrial processing applications. Secondly, there are also companies that produces PVT with air-based system. It means that that particular PVT produces electricity as well as hot air for space cooling in applications, and also for probably for drying applications. Drying is also one of the energy intensive industry. You need drying, you need low, what we call it, low to medium temperature drying, and PVT technologies are very suitable for this kind of application. So therefore, to answer your question, yes, there are companies. In one of my presentation, I showed you a PVT roadmap, basically for the European Union. The European Union has also embarked into this particular technology. What my interest is that because when I was doing my PhD in my doctorate in the United States in the 1990s, that's where I started to do one of the my thesis is about PVT. So therefore, it started then, and also when I was doing in the 90s. There are also various research that was carried out in this particular subject. I didn't know that now the things are picking up. And of course, when I did my PhD, it was a simple experiment, but then you have to actually innovate. And alhamdulillah, we have patented almost 5 patents in terms of PVT technologies. Now, the question is that the cost. There is additional cost. That number one, cost associated with the absorber tubes, the cost associated with the insulation, and then the cost is associated with even if you use nanoparticles and nanofluids. But these costs are not that expensive. Yeah, probably we are looking into the figure of about maybe 10% to 20% in terms of the cost. But the bigger picture is that you look at what are the extra energy that you get from the system. That extra energy will cover back your cost. In addition to that, as I mentioned earlier, that extra cost also will enhance your panel lifetime. So, and I've shown you a very as comparison to a conventional grid connected system with the various technologies for PVT, and you can see that there is a decrease in the payback period for that particular system, simply because the bigger picture is that that technology enhances the power, and when you get more power, you sell more power. When you sell more power, then you can get back your payback period as soon as possible. So it is like you are making a choice between buying one system which is very cheap and the other system which is very expensive. in the longer term, you will use all the necessary economics decision-making process to decide. You can use the payback method, you can use the LCA method for that. Using both LCA and the simple payback period method, you will know what to decide. So this is the one that I've shown earlier in my presentation, and you can see the cost effectiveness of it, and economic competitiveness of such a system. Now, another way is that to put, for example, putting a fins. What is a fins? Fin is a transfer device. You can see fins in a lot of applications. In your engine, in any call it energy conversion device, you will see fins. Even our nose is fin. Yeah, our ears are fin, because they are there for a purpose. They will cool your body. So sometimes fins are known as extended surface. It increases the area of heat transfer, and using fins also will basically cool down the pan. But you have to design the fin in such a way that it is actually in an optimal form. Not all will be done, and sometimes you have reverse effect. But if you design it properly, you'll be having a good way of basically transferring the heat from the base metal, for the base material to the what do you call it, to the environment. I would like to add one more thing. I've looked at one particular project that was done in one university, not in UKM, that he basically planted, the student basically planted some sort of herbs under the array of and that particular herbs basically decrease the surrounding, and it decreased the temperature of the PV. What is better to cool PV using that technique? You have both. You have also agriculture products, and you have also cooling of the PV panel. That is one, to me, one of the best method of cooling, and probably the student does not realize that he can make money from that. Somebody has to look at the report and say, somebody did a good job. And sometimes when you try to get what do you call it, a good solution to things, the simplest of them will be the simplest that we have never thought of it. And some of them don't realize that can make, that can make him rich.
Thank you, Prof. Dato. Actually, I'm also come across that kind of paper previously, whereby we can use the I can say the agriculture in order to help us in reducing the temperature of the PV. And when we talk about the cost, I remember one of Malaysia Malay thought that say that Allah membeli menang memakai. So we can spend more in advance in order to get a better income in the futures. Okay, so we go for the next question actually. Dear Professor, please explain the safety of PVT in terms of short circuit since it uses liquid tank. Liquid. Okay, thank you.
I understand. Mr. Very good question. Water and electricity never mix, right? But if you look at the system that we showed to you before, they are not connected with each other. We have an absorber tube that has liquid inside, so it is not in contact. Of course, people are also using PVT with jet impingement. That means you jet it to the surface. It is that PV panels has gone through thorough process. That's why they get the IEC certification. The IEC certification has nothing to do with the performance of that electricity. It has to do with the robustness of the PV panel. That's why you are assured to have PV panel working for the next 25 years. So if you look at IEC certification or the TUV certification, they are basically looking into several process, even putting hail, knocking hail on the PV panel. So and also weathering process. So if it can stand those things, so it's nothing for them to stand a jet of water. So so that's what I can say about that. But jet impeachment is only one way to do it. There are other ways to do it, but the other ways that I mentioned doesn't even touch the circuit of the PV. If you look at the back of the collector, there is a small circuit board. That black piece of we never touch it. The absorber pass around it. Yeah? So you have to design it in a way that sometimes we use even CFD to design the flow field. So the flow field are not in contact with the PV panel. So the issue of short circuiting or not, it does not arise.
Okay, thank you, Prof. So we can see that the safety already cater in this kind of research. So I believe it is very safe for us to go for this kind of technologies. Okay, do we have any times for the next? Yeah, we have another about 5 minutes, so we can spend another 5 minutes for another, I think maybe a last question here. So the question is from Budi Aprianda. Yes. Nice presentation, Prof. For PVT, if we see in company view, is a threat or an opportunities for the electricity company in the pricing aspect. Maybe Prof can comment on this thing.
Okay. I believe that it shouldn't be a competitive nature. Yeah? It should be a complementary nature. You have if you have cooling of the PV, you have very what you call stable power. You have increase in power. So and then it will go into the grid in such a manner that it basically can go into the grid sufficiently. So I would like to say this about this competitiveness. It's actually we are not in competition. Both technology are not. For example, the thermal part and the electricity part are not in competition with each other. Thermal has its own use. Electricity has its own use. Thermal are for industrial process heat application like water heating, space heating, space cooling. You can use heat also for cooling, and then also you use it for other low temperature industrial process applications. In terms of electricity, you know what is used. Yeah? It's directly into the grid, or whatever you need to do it for storage purposes, or whatever to be used later in the afternoon and night. The point here I want to make is that it is not in competition. It's actually it complements each other. I don't see that electricity company utilities will see it as a threat. You need it. Yeah? Basically, you need for your peaking power. You need for something for peaking power. Imagine during peak hours, you can use this instead of using the power stations. So in a large scale application, for example, in solar farm, you can see a 30% increase in production of electricity. That will be good for the overall picture in terms of the for peaking situation during peak powers. So that I want to add again, that I don't view it as a competition. I view it as complementing to each other, complementary to each other.
Okay, thank you, Prof.
The same view I also hold for renewable resources. They are not in competition. There are people who talk about such and such renewable as if the other renewable are useless. No, they have their own place. They have their own strength. They have their own advantages. And if used in a proper manner with an optimized condition, optimized mix, they will be better for the environment and better for the for emission reduction, and also for the overall increase in renewable energy mix for the nation.
Yeah, thank you, Prof. Dato. Okay, yeah, I'm totally agree regarding the complementary from either from PVT technologies or from the renewable energy, whereby the peaking will help the grid, especially during the peak hour, in order to reduce the tension of the grid itself. Okay, so again, thanks Prof. Dato for joining us today. Thanks again for the great sharing. I'm sure it will benefit us. Yeah, but it will benefit us in many ways. Okay,
Thank you
I
also
guess
for the challenging questions that I have to answer just now. I hope I answered all of them.
Yeah, I guess we have come to the end of the sessions. Thank you everyone for your participation. For your participation. I will leave everyone with a quote from Steve Jobs that say innovation is the ability to see changes as an opportunity, not as a threat. Okay, for that's all for this session. Before we leave, there are some housekeeping announcements here. Do catch with us with upcoming activities, events for today. At 2 p.m., we have a forum session on energy transition and the energy workforce, the roles of human resource management. The speaker for the sessions are Mr. Wahizan bin Abdul Rahman, Chief People Officer, Group Human Resource TMB. The second speaker is Farihana Hanafia, SVP Group Human Resource Management at Petronas. And the third speaker, Wisno Satrijono, the Executive VP of Human Capital Strategy, PTPLN. And then for the last session today, we are presenting Miss World Malaysia 2008, Dr. Su Winchi, that will talk about I'm also quite have a difficult to pronounce this, invincible energy, the spirit of not giving up. So hopefully everybody will catch up all the sessions for these evenings. So then that's all from me. Bye bye.